Okay, this is video number 2 for Chapter 8. In this video we're going to talk about finding an estimate for a population mean when we don't know anything about the population standard deviation. And this is usually the case. So this is more commonly used than the last method we talked about. In this case, instead of using the normal distribution, we use a different distribution that's actually called the student t distribution. So our critical values, instead of z of alpha over 2, are going to be t of alpha over 2. And we'll have a little bit different methods of finding those. So again, if we're going to estimate a population mean, we have some requirements. First is that the sample has to be a simple random sample. And the second one is that either the original population has to be normally distributed or the sample size has to be greater than 30. Here's our notation. We still have the same notation for the population mean mu, but notice in this case we're using S, the sample standard deviation, since we don't know sigma, the population standard deviation. We still have x bar as the sample mean, n is the sample size, e is the margin of error. Alpha is still the same related to the confidence level, and this time our critical value is going to be t of alpha over 2. Our margin of error is going to be our critical value times the sample standard deviation, s, over the square root of the sample size. So again, notice right here, s stands for the sample standard deviation. We find our upper and lower confidence limits the same way. We take the sample mean minus the margin of error and plus the margin of error. Now, to find our critical value, t of alpha over 2, our first two steps are the same as they were to find the critical value from a normal distribution. So we find alpha and alpha over 2 the same way that we did before. In this case, if we're trying to find the critical value for a confidence level of 95% and a sample size of 75, we go through and find that alpha over 2 is 0.025. Now, here's where it changes a little bit. For the t distribution, we not only need the probability, or the area, but we also need something called the degrees of freedom. And for what we're going to do in this case, our degrees of freedom will always be n minus 1. So it's our sample size minus 1. Now there's a function on your TI 83 or 84 calculator that will give you the t value if you put in the probability and the degrees of freedom. So that's inverse t, and all you have to do is put in your alpha over 2 of 0.025 and your degrees of freedom. You should get a value of negative 1.9925. Now if you're using a table, there is a t table that's on Angel, and what we're looking for is the area in one tail, and the column heading we're looking for is 0.025. Then we go down on the left side and look for the row labeled with degrees of freedom n minus 1, in this case 74. And some tables don't give all of the degrees of freedom, so in this case if you don't see a 74, there will probably be a 75, and you can use that to estimate your t value. It comes out fairly close to what we got with the calculator, but this table will always give you a positive value, so we get t equals 1.992. For the last step, in step 3, if you used your calculator and got a negative value, just change it to a positive value, and that's your t of alpha over 2. So in the end, we get our critical value is 1.9925. Or if we use the table, we get 1.992. Now we're going to construct our confidence interval. We want to verify that our requirements are satisfied and find the point estimate, the sample mean. Next step is to find our critical value. So in this case, again, we're using the t distribution instead of the normal distribution. And then the next 3 steps are the same as before. We find our margin of error, we subtract it from and add it to our sample mean to get our confidence interval limits, and then we can write our confidence interval in either of these 2 ways. Here's an example. In this example, we had 33 subjects that were treated with doses of garlic to see whether it would affect their cholesterol levels. Their cholesterol was tested both before and after the treatment, and the value that we're looking at is the net change in the LDL cholesterol level. The sample mean for the change in the LDL levels was 0.4, and the sample standard deviation is 21.0. We want a 98% confidence interval for the mean of the net change in the LDL cholesterol. So one of the questions we have to ask if we're trying to find a confidence interval is, first of all, what population parameter is it that we're trying to estimate? Well, we want a confidence interval for the mean, so we're trying to estimate the population mean for the net change in the LDL levels. This actually gives us two choices of formulas to use to find our margin of error, and we have to decide which is the right one in this case. Here's the one that we looked at in the last video, where we used the normal distribution and we had sigma, the population standard deviation. The one that we just looked at, we have our critical value coming from the t-distribution, and we have the sample standard deviation. Our next question is, do we know a value for the population standard deviation sigma? If we do, we can use the formula on the left, but if we don't know a value for sigma, then we have to use the formula on the right. In this example, the only standard deviation we have came from the sample, and that's S. So we're going to have to use the formula on the right side. So to construct our confidence interval, first we'd want to verify that our requirements are satisfied. We can assume that we have a simple random sample, and our sample size was 33, so it's bigger than 30. We had sample statistics given in the example, so our sample mean is 0.4. Now to find our critical value, our n is 33, so the degrees of freedom is going to be 32. And for a 98% confidence interval, our alpha would be 0.02, and alpha over 2 is 0.01. If you're using your calculator, use the inverse t function, put in 0.01 for the probability, 32 for the degrees of freedom, and you should get negative 2.4487. If you're using your table, you would want to look under the column for area under one tail that's labeled 0.01 and look for 32 degrees of freedom on the left side. You should get 2.449. Using these values and our formula for the margin of error, here's our critical value, here's our sample standard deviation, here's our sample size, and if we calculate that, we get a margin of error of 8.9515. To find our upper and lower limits for our confidence interval, for our lower limit, we're going to take our sample mean and subtract the margin of error. Notice we get a negative number here. That's okay, because what we're looking at is the net change in the cholesterol levels. If that's negative, that means that the cholesterol level actually went down. Our upper confidence limit is going to be 9.4. Our confidence interval, we can write in either of these two ways, as an inequality or as an interval. Now, to interpret the confidence interval, we are 98% confident that the limits of negative 8.6 and 9.4 actually do contain the true value of mu, the mean of the changes in LDL cholesterol for the population with the garlic treatment. Because 0 is in that confidence interval, it's possible that the mean of the changes in the cholesterol is 0, which would suggest that the garlic treatment doesn't change the LDL cholesterol levels. So the results from the study don't support the claim that the garlic treatment is effective in lowering cholesterol. In the last video, we saw this formula for finding a minimum sample size. The question in this case is, what if we don't know the value of sigma? What if we don't know anything about the population standard deviation? This is the only formula that we have to estimate sample size. We would be doing this before we actually start a study. So we don't have any sample data. We can't put in a sample standard deviation. All we can do is estimate a value for sigma. This is called a planning value. And one way to do this is to make a guess about the minimum and maximum data values that we might get from the study, use those to estimate the range, and then use what we call the range rule of thumb, which says that an approximation for the population standard deviation is the range divided by 4. Here's an example. For a particular model of auto, a study is going to be done on the miles per gallon. If we want to have a 97% confidence interval with a margin of error of 0.75 miles per gallon, how many automobiles should be tested? So what we're asking is, what does the sample size need to be in order to get that confidence level and that margin of error? Here we don't have any information about the standard deviation. So we will have to find a way to estimate that. So to use the range rule of thumb for this, what we would do is estimate a minimum MPG and a maximum MPG. And these, in this case, are really just guesses. So I estimated the minimum MPG might be 23 miles per gallon and the maximum might be 33. That's going to make our range 10, and if we divide that by 4, we get 2.5. So that will be our estimate for the standard deviation, or in other words, our planning value. Now we need our critical value. For 97% confidence level, that turns out to be 2.17. And if we plug those things into the formula, we end up with 52.3. Notice that in the formula we have our critical value, our planning value of our standard deviation, and the number in the denominator is the number that we want for the margin of error. When we get our value of 52.3, we have to round it up to the next largest integer, so it would be 53. Here are a couple things about the t-distribution, since we haven't looked at this before. The t-distribution looks a lot like a normal distribution, but it depends on what the sample size is. So it's again symmetric, it has a bell shape, but in a lot of cases it's used when we have very small samples. So there's more variability. But like the standard normal distribution, it has a mean of 0, so that's in the middle of the bell shape, and the standard deviation varies with the sample size. It's greater than 1, but as the sample size gets larger, the t-distribution looks more and more like the normal distribution. So here's a picture. These are the t-distributions for n equals 3 and n equals 12. So you can see the blue graph is a standard normal distribution. The red one is the t-distribution with n equal to 12. So that's really pretty close to the normal distribution. So as n gets larger, the graph is going to get closer and closer to a normal distribution.